Record.
Hey everyone, thanks for stopping by for my presentation. It'll be regarding the environmental impacts associated with hydroelectric power today. Um, so we're going to briefly cover what the problem is, generally, give a really high level overview of some of the problems with hydroelectric power. I'll try and contextualize the situation a bit more by giving you guys a little bit of history. What are the benefits and services we get from these facilities? Where hydropower fits in our modern structure today regarding energy. And then we'll go a little bit more deeply into those environmental issues before I try and offer any conclusions. Broadly speaking, dams and hydroelectric facilities today cause extensive ecological disruption. And it does that in a variety of ways that I'll get into later. But I mean, when you think about it, it's a huge wall that kind of blocks what I would consider to be a highway in nature. So of course, there's going to be some pretty big ramifications. Part of that is from the scale of dams today. Other things are from its needed infrastructure and its operation. There's a lot of emissions associated with their construction. I mean, look at the amount of concrete in that dam. And then downstream, there's the risk of dams breaking and huge loss of infrastructure, human life, and perhaps valuable productive land. But it's not like we build these things to hurt ourselves. There's obviously things we get in return. The biggest one today being electrical power. It's a big one. Another heavy hitter would be water supplies. Rivers have fresh water, and that water supply is really crucial, especially as fresh water is getting more scarce in the modern era. It's used agriculturally, residentially, and industrially, so it touches a lot of industries. It's very all-encompassing. And all of those places use electricity too. So it provides these kind of integral services for big parts of our economy. And then there's flood mitigation. We can prevent damage from happening to our communities downstream. So instead of having to build those villages, towns, cities, what have you, in a manner that can convey floodwaters and handle floods, you can concentrate all of that by making the floods avoidable through the dam. So you can build the cities and towns without all that flood mitigation infrastructure. You just put the big wall upriver. Given the historical prevalence of hydropower, not hydroelectricity, it makes sense that we rely on dams and hydropower facilities for so much. Back in the day, I guess 2 millennia ago was probably some of the first signs that we've found that hydropower was used. We have the Archimedes screw, which was used by ancient Egyptians and ancient Indians, not Native Americans, people from India is what I'm referring to convey water to a higher elevation and then use that for irrigation. The Romans also used Archimedes screws to pump water out of mine shafts. Then there is the water wheel. That's probably what everyone else thinks of when they associate old hydropower. That takes a structure that turns from the flow of water and it drives a central shaft. And that central shaft usually turns some kind of device that will process agricultural harvests in some way. I think the most common example would be to grind wheat into flour. But you can use mechanical energy to perform these labor-intensive tasks and increase productive output. And then at the turn of the 19th century, right around the beginning of the 20th, the shaft-driven electric turbine fit right along with that mechanical power coming from a water wheel shaft, and coupling them together made a system where you could transport the power of the river much further. One of the biggest challenges before the electric turbine was transporting that mechanical power derived from essentially really sophisticated water wheels. You couldn't really transport that mechanical power very far, and that was a challenge. So it was a big game changer for the electric turbine, which coincided with alternating current electrical transmission, which allowed us to transport power a lot further. So as an overview for modern hydropower, here are some of the aspects of it. If you start from the upstream side, there's the big reservoir that dams build, and that helps them keep a store of water so that they can continue with a steady generation of electricity, even when the river's flows maybe experience some variation. At the inlet or the intake, there's a control gate that can adjust the amount of water flowing through. There's also they call it a trash rack here. Sometimes it's just a screen or some metal bars in a cross grid. It just prevents debris from getting in. And that pressure and elevation energy gets converted into mechanical energy as it runs down the spillway. So I've added a couple arrows in this slide to show on that reservoir that potential and pressure energy pushes through and then gets converted into kinetic energy, which runs into the turbine and converts the kinetic energy associated with the flow of the water into kinetic energy with the turning of the shaft. And that converts the mechanical energy into electrical energy, which is where the arrows turn yellow, and it gets pushed out by the transmission infrastructure after being stepped up at a transformer. That just makes the voltage of the electricity a lot higher so that it can go further distances and reduce losses. A couple other notable pieces of infrastructure here are the spillway, number 12. That allows the dam to let water pass without generating electricity. Maybe the demand is lower, or they're doing maintenance on a power, or one of the powerhouses or the turbines. Either way, there's lots of reasons to be conveying more water than you can pass through your turbines. And then there's a fish ladder, number 12. It doesn't really look like a fish ladder in my opinion, but that allows migrating fish to go up river past the dam and get past the giant wall in their way. Yeah. And then in the realm of our overall energy infrastructure, hydropower contributes about 6.3% of the United States' electricity generation. That's a non-trivial amount. That's a lot. I mean, it's more than that's more than solar. That's more than biomass. It's more than geothermal. It's not as much as wind yet or anymore, but it's still a huge amount of electricity, and it's clean, right? It's considered renewable based on the water cycle, and it has no emissions or associated emissions with its operation. When you zoom out and think globally, hydropower actually jumps up to almost 16% of the global electricity production portfolio. And when you zoom out to total energy, it goes to something closer to the US figure for electric generation. It's like 6.4% there, yeah. So hydropower, broadly speaking, is a big contributor to our use of energy or generation of energy in the world. And the last thing I want to touch on is just the scale. I already had a picture of the Three Gorges Dam earlier in this slide for those of you that are familiar, but this is the largest dam in the world. It has a generating capacity of 22 gigawatts. For reference, the United States' largest dam, the Grand Coulee Dam, has a generating capacity of only 6.8 gigawatts. And even then, it's hard to appreciate the scale of this project. This thing is over a mile wide or long, however you want to define that dimension, 7,700 feet, and it's almost 600 feet tall. So this thing is colossal. It's so big that when it was completed, NASA calculated that the shifting of the mass associated with the water on the high side, the reservoir, relative to the low side, increased the period of the Earth's rotation by 0.06 microseconds. So they moved so much mass that the planet spins slower now, because it increases the moment of inertia by taking the mass away from the middle, for those of you who didn't know about physics. Crazy, it's huge. The point is the scale of these dams is so big that it is almost inevitable that it's going to cause some kind of ecological disruption. You're changing so much about the natural built environment in this area that the local ecosystem just can't function the same as it used to. So let's get into some of those ways that it's being disruptive, right? We'll separate it by the upstream, downstream, and construction effects. The upstream issues are essentially centered around the disruption of the reservoir. A reservoir has much slower water speed, so the water has more time to absorb sunlight. It also raises the general elevation of the water, so the surface area of the river increases. That causes it to absorb more sunlight, and it creates a net rise in the temperature of the water that's stagnant in this area. That net rise in water temperature also increases the evaporative losses of water from that reservoir, and it can increase the salinity, the salt content of the water upstream. All of that creates an environment that's not as familiar to riparian species. Riparian just means along the water's edge and in the river. These river ecosystems are no longer the same as they once were. And so the species that would flourish in the river ecosystem struggle, and it creates openings for invasive species that are better evolved to handle lake ecosystems. They are able to invade and kind of displace the native species. And that's essentially a net loss of biodiversity, that underlined point there. Biodiversity loss is something that people hear about a lot, and they probably ask, why should I care about this? Like, why is this net bad for me? And there's a lot of reasons, but the quick and dirty is that ecological disruption, biodiversity loss, does not just affect your area. It affects how your ecosystem functions and usually changes it for the worse. By that I mean it's either less productive, there's lower species richness, there's a less number of species, and it can't function in the way it could before. But also, your ecosystem, the one that's being affected by all these changes, interacts with other ecosystems extensively. And that's where it gets a little bit murkier. For example, migrating salmon populations in the Northwest have had their life cycle seriously disrupted, the last point here, by these dams. It's a giant wall in what was once their highway to get to their old spawning grounds. So it prevents them from getting to their spawning ground and completing their life cycle. And the net result is a decrease in the population of salmon. In some areas, it's 90%, the spawning grounds that are furthest up the Columbia River in the Pacific Northwest. That causes a obviously net reduction in salmon populations. But when those salmon migrate downstream and they exit the Columbia River to the Pacific Ocean on the West Coast, they're eaten by orca and killer whales. So they serve as a food stuff for this other species that is a major aquatic predator. Killer whales are notorious. Predators are important in ecosystems as they maintain balance. For example, those orca whales might be eating other species that are herbivorous. They eat plants. And without the orca whales supporting their population with salmon, there's going to be less of them hunting. So those herbaceous or herbivorous species that the orca whales are eating are now able to proliferate. There's a lot more creatures eating local greenery in a different area because these predators aren't eating as much salmon. And so those ecosystems start to get thrown out of balance because there's out of control consumption of the plant life in the local area. And so it continues to ripple outward from your ecosystem through your ecosystem's connections to the other ones. And it doesn't necessarily just have a local impact. And reduction in ecological function and productivity is part of the reason we are in our kind of environmental crisis. Obviously, the main thing is emissions, but those emissions are hurting us by eliminating biodiversity and making environments more difficult for species to survive in. And it kind of breaks down ecosystems bit by bit. It's very gradual and difficult to track. So these effects, I'm taking a little extra time on this slide just to give you a bit more of an understanding on how deep the disruption can go. Also, that point, river siltation. The natural composition of solids in the river is kept at certain levels by the river mixing them around and flowing. And on the high side of the dam upstream, all of those solids kind of fall to the bottom of the riverbed. That's the process of siltation. And it changes the mineral composition, the solid portfolio, whatever you would like to call it, of the water that passes downstream. And that can additionally disrupt the ecology and make it harder for native species to thrive. So downstream, it's kind of the same story, right? All of that warm, low oxygen content water that's extra salty and I guess I already said it was higher temperature, that gets passed through the dam and is now jettisoned from the lower side at really high velocity. Those high velocities make it harder for species that are, swimming in front of it. It can be dangerous, but it's also eroding the river bed. It can change the cross-sectional profile, changing how the river flows, changing how species interact with the environment, further environmental and ecological disruption, further biodiversity loss. There's also risk to human populations, as I said before, from dam failure. Between 2005 and 2013, there were 137 recorded dam failures. Most of them were due to a phenomenon called overtopping, where the water in the reservoir is just spilling over the top of the dam. And that's usually caused by especially heavy precipitation events or a dam failure that happens upstream and allows a lot more water to go past. That phenomenon of overtopping stands to increase as climate change gets worse, because climate change makes precipitation patterns within the water cycle a little bit more erratic and more extreme. So as snowpack melts with higher alpine temperatures, with global warming, there's less of that bank of frozen water in the mountains, creating a steady precipitation profile, a steady flow profile down the river. And more of it comes down just as liquid water from the clouds all at once. And so these dam failures might increase over time, putting communities at risk that are downstream from them. And then another specific ecological disruption I wanted to highlight was how migratory fish populations are further hurt downstream from the way that fish bypass infrastructure works. So on the left side of the graphic, you can see here, there's a really steadily ascending switchback with little discrete units in it. That is the fish ladder that allows mature fish that are trying to spawn, coming from the ocean, going upstream. They use that to go past the dam. But juvenile fish, after the spawning has occurred, need to swim back down the river and go out to the ocean. So fish bypasses for that are usually just a net that runs across the front of the dam and sort of encourages the movement of juvenile fish towards an intake, and then it's just a pipe that blasts them out on the other side. It'll probably go clear of the dam, but the point is, all of those juvenile fish migrating downstream get concentrated in one area, and bird populations and other fish populations that prey on those juvenile fish now have a concentrated area to gobble them up, and they no longer have to patrol the run of the river as much as they used to get full meals. That is more ecological disruption, resulting in more fragile ecosystems and that sort of rippling damage and change that can throw ecosystems out of balance. It's just one more chink in the armor, one more chip away at the robust resilience that ecosystems typically have. And then the construction of dams has essentially a lot of associated emissions. To make a dam, you use so much concrete. Insane amounts of concrete. The Hoover Dam had something on the order of 4 million or 4 to 5 million cubic yards of concrete used. And the cement that goes into concrete is the especially carbon intensive ingredient. Some estimates have 1 cubic yard. Remember, there's almost 4.5 million of these in the Hoover Dam. 1 cubic yard of cement can produce up to 400 pounds of carbon dioxide emissions. That's huge. So building less of these would definitely drive down overall emissions of nations. And then once you build a dam, you can't just let it sit there. You got to transport the electricity out of it. And that transmission infrastructure also has a lot of associated construction emissions. Aluminum can generally produce just under 12 tons of carbon dioxide for every 1 ton of aluminum produced. Steel's a bit more friendly. It's closer to 2 tons of carbon dioxide for every ton of steel produced. But even with those emissions, there's further ecological disruption caused by these transmission lines. They, kind of crisscross across the nation, and they slice up what would be large continuous habitats for animals that use larger territories, greater predation areas that they patrol, or just they need for their life cycle a huge land area. When that gets fragmented, it interrupts their ability to function, and big surprise, can result in biodiversity loss and ecological disruption. Also, the habitat is just straight up destroyed along the path of the transmission line to clear the way so that there's nothing getting in the way of electricity and grounding it out. So what do you make of all of this? How do we move forward? What conclusions can we draw? So the benefits are clearly there, and we rely upon them heavily. The electricity generation is really important, especially as we're trying to proliferate green and renewable energy sources. The water is becoming increasingly valuable. Fresh water is getting more and more scarce throughout the world as global temperatures rise, and evaporative losses continue and droughts are exacerbated. I mean, the Southwest US is in a mega drought right now, and dams provide a lot of the water for that area. So, it's a valuable service. And then that flood control, we haven't built a lot of communities downstream of dams to handle the flooding that would naturally accommodate the river if the dam wasn't there. So if we do decide to remove dams because they have these profound profound environmental impacts, you have to consider how you're going to replace those services. That doesn't mean removal is impossible. I think removal personally should happen anywhere that it is deemed plausible, where we can replace the services and where the environmental damage caused by the dam is especially bad, like in the Northwest, where fish populations have continued to decline. That replacement of services is probably going to happen with something like a large solar or wind farm, whatever the greatest local renewable energy resource is. You kind of have to build that out to compensate for the loss in generation, which is significant from these dams. To replace the water infrastructure would mean implementation of some kind of new way to harvest and distribute water from the river. I'm sure you could do that in a much more ecologically healthy way that does not create a wall across the entire cross section of the river. And then flood control means that you got to build cities to handle flooding. That's probably a really expensive aspect of removing dams. And then the actual process of removing a dam is not trivial. You have to do it in a way such that the dam doesn't break and fail and flood downstream, killing everyone else. On the downstream side, you have to do it steadily. There's a lot of engineering and planning involved. It's expensive and difficult. That is where we stand in the US. We have a ton of dams in the US. So our only option is to either keep them and maintain them or remove them where they're doing the most damage and try and replace things. Around the world, there are something on the order of 3,700 hydroelectric projects in various stages of planning or construction. Obviously, not all of those that are in stages of planning will come to fruition and get constructed, but the best tool we have facing those dams is careful planning. The planning process and the environmental assessment associated with dam implementation has become so much more in-depth and comprehensive that we're able to optimize the balance of environmental damage versus what is most convenient economically and socially for human infrastructure. Where can we transport the power the least and have the biggest reservoir? Where is it geographically convenient? those planning processes have incorporated much, much, much more environmental aspects. So maintaining the rigor of those environmental assessments internationally by maybe offering consultation from countries like the United States, where we have a long and mature history with hydropower. We're aware of the problems that comes with it and where you should put the dams. That sort of expertise should be exported to developing countries that are aggressively implementing hydropower, like in Brazil, so that they aren't making some of the same mistakes that we made perhaps while we were still learning about hydropower. And then changing how we think about hydropower. Instead of calling it so renewable, I mean, I think it's well understood that there are a lot of caveats with hydropower. Just categorizing power or electricity generation by renewable versus non-renewable maybe is a bit oversimplifying the problem. And we should acknowledge that all forms of energy generation have negative environmental impacts, and there are certain environmental impacts we're willing to live with and certain ones we're not. Like emission of carbon dioxide is especially bad right now because that is causing not only global pain, but it's driving a lot of other environmental damage. So maybe just thinking about these different generation sources, perhaps on a gradient or a spectrum, and trying to implement the ones that are least damaging more than the ones that are damaging, like hydropower, would be really beneficial to our planning methods and implementation of hydropower. And finally, as a little bit of perhaps a rip from my discussion section from my paper, from a speculative standpoint, I haven't put a ton of research into this prospect. I was thinking that following the trend of distributed electrical generation, so we learned about this earlier in the quarter a little bit, how everyone is buying solar panels and putting them on their house, and other small sources of generation are being introduced to our grid, which was designed to handle a specific point source that generates a lot of power and then pushes it out onto the grid where everyone else uses it. Now we see a bunch of little sources of power, and we're modernizing our grid very slowly to try and handle that change in infrastructure. Maybe hydropower can take advantage of that distributed generation trend. And as we maybe decide to dismantle some dams or dismantle more dams, we can replace them with smaller facilities that don't cut across the entire run of the river. Instead, we could divert a portion of the river's flow, dedicate that flowing channel to hydroelectric power, irrigation, and water storage. And it could act as maybe a flood buffer because it's an alternative path for the water to flow. Then we wouldn't be taking over the entire river. You know, fish could still swim up. We would still get power. We would have to create way more of these facilities to make up the scale that is so beneficial for us and disruptive for the environment. But it would perhaps be something of a happy medium where it's not such a huge, single massive disruption to the ecosystem that it prevents a lot of aspects of it from functioning at all the way that they should, like migrating fish. Just a thought. It would probably be really expensive, like all of the actions that make our energy infrastructure greener, but it's something that should be a part of a larger strategy, just like every part of renewable energy. It's all chipping away at the problem. Anyway, I start to digress. That is the end. Thank you for listening. I hope it didn't go on too long.